In this experiment called the concentration of citric acid in lime juice, we obviously wanted to calculate the concentration of citric acid in lime juice, and we wanted to argue why or discuss why we can say that there is citric acid in lime juice. We did this by doing a titration reaction, or by doing a titration. We did 4 different titration. The first one was a colorimetric titration with sodium hydroxide and just plain citric acid. We used phenolphthalein, which changes the solution to a like red color like this when pH is about 9. And afterwards we did still with the sodium hydroxide and just plain citric acid. We used a graphical analysis program for the pH, and we used a pH meter to calculate the pH value, so we could kind of see, the correlation between the two, and it was about the same. I think we used about 19.4 milliliters to change the color here, and it had an end point where it changed color at about 19.25 milliliters. So that was kind of the same thing. Afterwards, we did with lime juice instead of citric acid. We used sodium chloride, not sodium chloride, sodium hydroxide, and lime juice, and it looked kind of like this. And then with the red color in it, in the colorimetric titration, it was kind of the same. We used 17.6 milliliters for that, and in the titration that we did with the pH meter, we had an end point at the not 19 but like 16 point something. I don't really remember. 16.5, I think it was. No, 18. We had an endpoint at 18 milliliters. Yeah, at about we had an endpoint at about 18 milliliters, so that was pretty close too. Looking at the two graphs that were made with a program, we can see that they're not perfectly alike, but they're very much alike. They have the same kind of structure, which is one of the arguments why we can say that there is citric acid in lime juice. The thing is, the citric acid has this curve, this titration curve, when we calculate pH, because oh yeah, those are the two different endpoints. It was 18.5. Looking at the reaction schemes, we can see that this is the first reaction occurring, this is the second, this is the third, and for the first reaction we have normal citric acid here, and it is in an equilibrium where it makes this is a non-strong acid, it makes a weak acid, so this is still an acid, and then it turns into another acid, which this acid turns into a weak base. So this is actually when it changes its pH value, when the endpoint is reached. That is at the third reaction. So we can't see the first two endpoints, but I've marked them here. The thing is that, as we can see here, not here. Oh yeah. For the citric acid, for all the NOH that was used up until the end point, we have used citric acid 3 times, the same amount of substance, because we have the first amount here, the second here, and the third here. That is why when we calculate later the concentration and we calculate the amount of substance, we have to divide the amount of substance for the for the OH minus ions with 3, so we get the amount of substance for the citric acid, only the first time, because there's really only citric acid in the first reaction. This is no longer like real citric acid, it's a different kind. Going into the calculations, we had to, for finding the concentration of the citric acid in the lime juice, we first had to find it in the first titration, which was with normal citric acid and not lime juice, so it was only sodium hydroxide and citric acid. As you can see here, we used just a general concentration formula, and this is for the OH because we know that the amount of substance will be a third. The citric acid, the amount of substance for that would be a third of the NOH. We have to first calculate the NOH, and we did that here and put it into the formula here. So we got the amount of substance for the citric acid, and then we could use the concentration formula again. We only added 25 milliliters of citric acid, so it's a new volume, and we got the concentration, which was 0.026 moles per liter. And the first endpoint was found by dividing the total volume of the sodium hydroxide added by 3, because then we got 3 different equally big parts, like this and this. So they're added into, showed it here. The endpoint was at 19.25, and therefore we have the other endpoints at 6.4 and 12.8. So that's around here. And we need those different endpoints because those are the invisible endpoints that are there. We just can't see them because the the solution is still an acid. One of the other arguments you can use to say that there is citric acid in lime juice is by looking at the pKa values. They are, well, if you look at the different endpoints, I have made them here by making some lines. To find the pKa, you need to go halfway through that, and when you go 1/2 down, you get the pKa value. And for example here, if you take the first endpoint, the pKa value is about here, and we read it to be 3.72 pH, which means that the pK is 3.72, which is a little bit higher than it's supposed to be. And this is the data book, what that says it should be. We have, for the next one, the pK2, we have around here, it's about 9 milliliters. We have a pH value of 4.93, which is also a little bit higher, but not too much. And then we have the last one, which is at about 15 milliliters. We have a pH of 6.35, which is, again, it's closer. It's closer. So obviously they kind of follow the same path. They're very close, while not being perfect. Obviously, there are some errors to this experiment, and there are things that maybe the titration wasn't done exactly properly, and it's done all with eye measure, so you can't really control how much. It's hard to control how much sodium hydroxide is put into the mix. But it was almost it was supposed to be 0.5 milliliters every time, but it could have slipped just a little bit. So that might explain the kind of different pK values, but they are very, very close. And we can see the graph again. It looks very much like the citric acid. So Yes, I think I will move on to calculating the concentration of citric. So when we want to calculate the the concentration for citric acid and lime juice, I'm doing this because it's a lot easier for me, but we need to look at this graph instead of this one. This was the one we used before, but we're going through kind of the same calculations as before, where we look at the amount of substance and we calculate for the OH. It's exactly the same. It's just a different endpoint, so it's some different numbers. We do the same thing by dividing it by 3 and getting a number here, which is supposed to be like this. There we go. And then we need to calculate the concentration, but we diluted the lime juice with water. So we need to do something about that first. We need to take that into account, and I've done that down here by dividing the 20 milliliters of lime juice with the 230 milliliters of water and getting a number here, and that number times the 25 milliliters that we added for the titration, because we didn't use all of this, we only used 25 milliliters, gives us how much lime juice that were actually in the titration. It was not the whole 20 milliliters. So to calculate the concentration, we need to take that number, the number from before, 0.617 millimoles, divided by 2.17 milliliters, and that gives us 0.28 moles per liter. And as you can see, you know, the milli goes out with each other, so we have moles per liter, and that gives us 0.28. And looking at, let's see if I can do this. I googled it, and it says that for lemons and limes, and we did it for limes, it is 0.30 moles per liter. So it's pretty close. It's not that far off.